Okay, let's get started. All right, so let me get back to uh, what we've been working on. I had a get going stream this morning, so this is going to be a shorter stream. So let's open. Let me just go. Okay. So where did we leave it yesterday? We left it at we've got these unimplemented functions, and we have the tests that we need to implement, right? So I ran my test yesterday, and these all came back. Let's start with this one. So we do have, and again, I got to look it up now because it's been a hot minute since we did this. And also, believe it or not, the longer you're programming, the longer this stuff actually just kind of, you don't actually, I hate to say it, but don't actually remember everything you've done in the last few days. Because one of the things that happens with memory is your brain takes stuff you've done before and compresses it. So we are going to go ahead and um, we do for metadata test. Okay, so that's just and so what we have back from this is a publish entity server, and we want to make sure that, do we check the type? No. Actually, if this is nil, we can stop, right? Expected a published entity. Sorry, not running a lot of sleep today because there was an incident at work that kept me there until 12:30 a.m. All right. And what do we expect? We expect the, right, we expect, oh, we do check the type. Now that's just testing for nil, I believe, because if we look at, yeah, that's an interface, so that would be testing for nil. So this we can say this is straight up error. There's no format there. Okay, if we run this, it passes. Okay, good. Okay, so let's look at implementing the testdb publish entities. Let's implementing create. So what do we want create to do? It's going to So in this case, we're going to expect an insert into something, right? So we're going to expect a query. What does this return? This will return and probably an ID column. Okay. So at this point, I don't know exactly what it's going to be, but I know it's going to call insert, and we're going to go ahead and create a new caller, right? And we're going to call create, and this is going to take an entity name, metadata, and this is going to have an ID, right? And it is going to return a published entity. All right. So if the error not equals nil, we can stop. Okay. So we expect publish entity identifier not equal to. So if the publish identifier is an empty string, then we've got an error. Okay. Uh, okay. So that takes a look at the identifier. So now we have key, we have ID. Oh, this creates context as well. Okay. Yeah, here's our first problem. Our first problem is we do have to pass the database context in. So it should be CTX, metadata, ID, and then the key for the thing. So let's go back to published entity and all these things. So let's go in here. So all of these need to take a context. This is the annoying thing about context, and there really, there's got to be a better way to do it, but I'm not sure what that is given the system, right? So what are we doing with context? So what's context doing? Context is um, context is passing a way for us to appropriately time out or cancel activities. This passing a parameter through everything is really clunky, and I don't know that there's any other way to put that. But I'm not exactly sure, given the context of the ecosystem, what we can do at this point. Let's say, for example, we had a timeout. Um, you might, yeah, I don't know what to do at this point, other than we've got to deal with context, and we have to pass context through on everything. Okay. So now we can pass context. So what is the first? Okay, p equals 0. If that's the case, the entity is a string. Okay. Also, by the way, still not sure about the visibility on the elements of key and the visibility of key. So what do we expect to have happen? Um, we expect uh, select. Um, let's just select ID from metadata where. So that's the query we're expecting. And this will return rows. And what are the rows that this returns? So let's take a look. It'll return the ID, date capture, location, and tags. Just return ID. Oh, okay. So at the very least, we're going to go in and grab an ID to show that it exists, right? Then we are going to do an insert. And we don't have a table for this yet. So let's take a look at publish entity and decide what this table is going to look like. So this table, and we're going to call it published entity. And Okay, so the first thing is we need an ID column, and this is going to be big int, default, val, and I want identity sequence. Okay, so this gives us our ID. Then we need identifier, and this will be a varchar, and this is there's no default value, but it shouldn't be ever null, and it should be unique. Okay, so the next thing, what do we have? We've got our key. So that consists of a entity, and that's a varchar. Again, shouldn't be null. Now this is the name of a table essentially, and there may be a place for a check constraint at some point in the future. Let's go ahead and add. Let's call this referenced entity. This is a big int, and this should never be null. Should it be unique? Let's think about this for a second. Could there be a case where we have multiple of these things for an underlying entity? I'm going to say there shouldn't, no, there should be a one-to-one correlation, so this should be unique as well. So let's take a look at our table again. So we've got, this is also the primary key. So we've got our ID, which is a big int, and it has this identity. We've got the published identifier, and we've got the referenced entity and the referenced ID. Is that stuttering? No, that's good. So okay, I think that's it. Let's go ahead and start with this. Let's go ahead and start with this. Okay, so we've got published entity. So we've got insert into published entity, and we are going to identifier ID. Let's make this a backtick string so we can span lines. Values. What do we think the identifier should be? How do we calculate a unique identifier. And what are the properties we want with this unique identifier? Here are the properties I think are important. One is it should be producible from some underlying data. So I should be able to consistently produce the same value given the same underlying inputs. Okay, so let's just make a little note of what we want here. What do from our generated identifier. So 1. I want it to be stable given a set of inputs, always the same output. No GUID. So GUIDs have a random, well, generally have a random component, and I don't want the output to be dependent on that random component. Okay. 2, I want it to be unique for the range of inputs, which is basically an int 64. 3, not guessable or incremented. So if I return back, if you create something in the database and then you turn around and get that thing and look at the ID and then go to create another thing in the database, you shouldn't be able to guess the next ID value from the one you just got back. Does that make sense? So if I create to something, I shouldn't be able to guess the identifier of the next thing. So it's stable. Okay, so that means if we, for whatever reason, lost the identifier component, if we ever lost the identifier, we could regenerate it, right? No, that doesn't make any sense. So yes, so it's stable. So given a set of inputs, we'll get the same output, unique, and so forth. Note that stable does not mean we don't have to store it. So for example, it could be two parts to this. There could be the ID of the thing that we have plus some seed, and that produces an output. But the seed may not be part of the application, may be stored separately. And lower no collisions. What else do we want? We want it short, so it can be typed. So this throws out things like a SHA of the number. because that's going to generate this huge big thing that would be difficult to type out. And I want something that, uh, even if it's 14 characters, be able to group it in like 7 and 7 or something, so that if somebody said, "Hey, look at blank," you could type in the identifier. So it shouldn't be something that's so big that's unwieldy to type out. And that's one of the things I don't like about GUIDs, is that they're so long that if you have to type out a GUID, it's just painful. So we want stable, we want unique, we want something that you can't guess. So like just taking an MD5 of the number wouldn't work, because if we just did that, you could easily generate an MD5 of, the first, billion or 2 billion or whatever IDs, and just check to see if, got a match, right? You could salt it. I don't know. But yeah, so I do want it to be short. So ideally, it wouldn't be any longer than, 15 characters. Yeah, 15 characters. We can do 3 groups of 5. Um, 14, we can do 2 groups of 7. Um, Generally, I'm going to start numbering over 1 billion. Um, so I don't, I don't want something that, I need something that can, ideally, it wouldn't change size with the number of digits. So let's say independent of digits. Independent of the number of digits. Independent. Yes, there we go. Independent of the number of digits, size of string passed in. So if I have a 4-digit number, the resulting ID is not going to be shorter than if it's a 10-digit number. Okay. Um, let's go take a look and see what the interwebs has for this. I think my computer just switched over to daytime. Nope, that violates my requirement for it to be.
The best way to become a
Nope, we're not going to watch a video. That looks promising. Okay. This might violate my guessing criteria, but let's take a look and see what they do. Okay, so we got some choices here. Hmm. So if we look at this one, the first one, time is good, no random bytes. 4 bytes of time plus 3-byte machine ID plus the process ID plus some random. Nope, don't like the random. 8 bytes of time. Then we got the random. Um, yeah, again, come back to a lot of these have a random component. So let's think about this. So if we add time, and we're going to go ahead and edit this table, modify table. We are going to add a column, created, and we're going to set that to timestamp. And not null, but no default. So we have to provide that timestamp. So if we want to use the low 4 bytes of time. Okay. So we time in millis. 2. The identity of the thing referenced. 3. Newly the name of thing referenced. So this is 4 bytes. This is 8 bytes. And let's say on average this is 12 bytes. So that is 24 bytes. But what do we want to do with this? All right, let's take a look at a couple of let's take a look at MD5 real quick. That's too long. It's 24 bytes. Reference ID, I think, is unique, right? Yeah, it's unique. So this actually can go away. So back down to 12 bytes. Okay, so we've got 12 bytes, which I know these values are going to be unique. What if I XOR them with a 12-byte number? So what if I have a secret that is a 12-byte secret? So and this could be random, but it's not random each time. It's random at the start of the system. I could pass it in, so we pass in a random seed. Then we XOR with 12 bytes random seed. Again, this is not encryption. The goal here isn't necessarily to evade the KGB. The goal here is to just make it so I've got a reasonably short identifier. So let's just create a new. We're going to call this test items. So we are going to do this. We're going to take okay, that's reasonably variable. So what is this going to return? This is going to return in64. And of that in64, we want the low 4 bytes of that. Actually, let's do this. 2, 3, 4, 5, 6, 7, 8, 9. So it's 8 bytes. So it'll be 16 of these things. A, B. Right? One, two, three, 4, 5, 6, 7, 8 bytes. Skip this for now. And it's the best way to convert this to. Let's go ahead and mask on okay. And this will be our test number. And this will be our mask. And what we'll do is we will say number and mask. These actually need to be unsigned integers, right? For what we're going to do, these need to be unsigned integers. Yeah. Let's see. EFCD, okay. I get a leading 0%, 0x. So 0, 2. Yeah, there we go. All right. Okay, so we want the low 4 bytes of the time in micros. Or, yeah, micros. Okay, we need a function. That function should look something like func grab int part to slice. And so this takes uint 64. I'll call this a number. Takes a uint 64 number bytes. And this returns back a slice of uint 8. Okay. So for 0 I less than oh, I gotta get going. I'll finish this later, but yeah, so if I pull back the slices, I should have an array of 8 bytes or 12 bytes, and if I XOR them against a 12-byte random XOR, I should have something that's unique, right? Because let's say I XOR a 1 and a 0. So if I know my key is 1, I know the resulting thing is a 1. I know the other one had to be a 0. If it's a 1 and the answer is 0, I know it had to be 1. If it's 0 and the answer is 1, I know the other one had to be 1. And if it's 1 and the answer, sorry, if it's 0 and the answer is 0, then I know the other one had to be. So yeah, Azor should be a completely unique mapping, if I recall correctly. So if we take the 12 bytes, then we XOR them, and then we base 64 encode the 12 bytes, I'll have a stable ID. So it'll be stable. It'll be in the sense that given the same underlying secret, given the same time, and given the same ID, I will always generate the same unique reference. There won't be any collisions. So going back to my, so let's take a look. Here's our algorithm. Our algorithm is take the low 4 bytes of time. That should be highly variable. Take the ID of the thing. Take a random seed. 12 bytes. XOR them. Base 64 encode result. So if I base 64 encode it, basically I'm saying I'm taking I've got 12 bytes, and I'm using that's 96 bits. That winds up being 16 characters, and split into 2 groups of 8. So I should have no, not base 64. Base 64 is too hard to type out. 3 groups of 8. X into 3 groups. So for these, I'm willing to use uppercase and lowercase letters and numbers. So that's really base 62. Anyway, encoding, worst case encoding, I'll have 24 characters, which could be divided into 3 groups of 8. Which is longer than I like. If I reduce the time to 2 bytes of time, if I reduce the time to 2 bytes of time, if I reduce the time to 2 bytes of time, that gives me 10 bytes, which I then need to XOR against 10 bytes, which gives me 20. It's going to be 4 groups of 5. What if I lop off the two? No, I don't want to lop off. I could lop off. I could lop off 2 bytes. What if I did 2 bytes of time and then low 6 bytes of the identity referenced? So what would happen here? So I have the 2 low bytes of time in milliseconds. So this repeats, this has a period, this would have a period of 65,000 milliseconds. So 65,000 milliseconds is 65 seconds. So it would cycle every 65 seconds. So every little bit more than a minute it would cycle. What if I did seconds? So this would cycle roughly every 18 hours. Oh, anyway. I think I have my basic algorithm. I don't know if it's as short as I want it, but it would be stable. It would be unique, especially if I use the 8 bytes of the ID. I know it would be unique. It would be difficult to guess, and I couldn't just increment it. I'd have to, you know, um, what if I use the low 3 bytes and the low 7 bytes? We'll use millis. So that would be every 256 minutes. So that would cycle every 4 hours and change, 4.5 hours. So we'd have, let's cycle every 4.5 hours. And I doubt I'd ever use that top byte of the, so the first bit of the identifier is wasted because it's signed, right? It's for the signed. So these are the next 7 bits. Yeah, I think I can use the low 7 bytes out of the identity. No problem. I'd probably use the low 6 bytes to be honest with you. We could do the low 7 bytes. This would be 10 bytes. And if I restricted it to, um, if I restricted it to just letters, so 52, and we get rid of, how many letters I want? I want 16 letters. So instead of hex, we use just letters to encode it. We use just letters to encode it. That's base. It's essentially base 16. So if we did base 16 with just letters, That would still be 20 letters. What if we did, so we 10 bytes. What if, so if we used uppercase and lowercase, we used 32 letters. We use 32 letters. That means we have 5 bits. So 10 bytes is 80 bits. So it could be represented in 16 characters. So 2 groups of 8 characters, upper and lower case, using only 16 characters of the alphabet. Five bits per glyph. So here's what we could do. So this is what it's looking like our algorithm is. So take the low 3 bytes, low bytes of time in millis, low 3 bytes, low 7 bytes. That gets me 10 bytes, right? So I XOR it with a random seed. If there's a 1, you know the XOR with either, if you have a 1, yeah, so it wouldn't, I don't think it's going to fool the CIA, and I don't need it to. I just need it to be good enough so that um, someone can't just iterate through the IDs by incrementing a number. So this would be like A, D, K, J, F, B, Z, N, Q, R, A, D, K, F, B, Z, Q, R, dash. To something like that. if I used all, so that's 32, I could go to 64, but I would use upper and lowercase letters of the alphabet. So that would be 26 plus 26 is 52. I would use the numbers 1 through 10. And I would only be shortening it from 16. So if I base 64, I'd be at 6 bits per glyph, 80 bits total. Um, well, 6 doesn't evenly divide into 80. Um, it would be 13 as opposed to 16. 13 and a third. So most of them would be 13, but some would be 14. That's not much of a shortening. I'd rather have them the same size. Or it'd be 2 sevens. At this point, I'm not trying to make it more unique. At this point, I'm trying to make it easier for someone to read over phone. Hmm. I think that's good for now. Anyways, I going for it. All right. Excuse me. See you tomorrow.